stuff here. In order to, I kind of got some stuff from first period here, so we're going to try and get through this as quick as possible, get some books, get some paper out, and let's write some stuff down here, guys. So, first things first, what we need to know from Unit 1. We need to tell you how many protons, electrons, neutrons are in an atom, for example. Okay? How many protons, electrons, neutrons, and atoms? So I just picked a few. I'll try and give you examples where possible. Okay? And we'll go from there. Okay? So I picked calcium, for example. Calcium, of course, is number 20 on the periodic table, so 20 protons, right? 20 protons. It's a neutral atom, calcium. In this case, I know that because there's no charge on this calcium. And I got 20 electrons, therefore, so 20 positives, 20 negatives. They cancel each other out. The weight of calcium is 40.08. So we're going to round it to 40, right? And we're going to take that 40 minus the number of protons, and that would tell me how many neutrons I have, okay? Which works out to be 20 neutrons, of course. So remember, protons and neutrons have to equal the mass. Protons and neutrons have to equal the mass. Okay? Maybe I'll write that down somewhere here. Protons plus neutrons equals atomic mass. All right? If I give you an ion, remember what happens in an ion? Well, it's either gained or possibly lost electrons to make a more stable atom, basically. Well, which with a charge, ion. So in this case here, we have, actually, let me do this here. I don't want you guys cheating here. Because you're just going to write stuff down here. If we got sodium ions, for example, sodium is always number 11, doesn't matter. Always number 11 on the periodic table, so it's 11 protons. This one has a 1 plus charge, so remember, we've lost an electron. That's what that means. So we have 10 electrons in this one. Because remember, it's 2, and then it's 8. Stable, octet rule. Okay? And then, of course, don't forget, the protons and the neutrons equals the mass. Yes? So in this case, sodium is 22.99, so 23. So 11 and 12, 23. Okay? So that's the first thing we probably need to review there. Okay? Good? Yes? All right. Next. Names of the groups. We need to know all the names of the groups. Okay? This is something you should always know. Okay? Not just for this. But group 1 is called the alkali metals. Okay? Group 2, alkaline earth metals. 3 to 12 are called the transition metals. I have to do this very, very quickly, so that's why it's very, very messy. Group 17 is halogens, and group 18 is noble gases. All right. Okay, I don't think I'm going to ask you this, but once again, in your notes, 4 properties of metals versus nonmetals, such as, what are, you'll find them, they're right at the beginning, guys, but 4 properties. Metals tend to exist as solids at room temperature, nonmetals tend to be solids, liquids, gases. Metals are malleable, ductile, and nonmetals tend to be dull and brittle, okay? Metals are shiny and malleable and all that stuff. Metals exist as atomic elements. Nonmetals tend to exist as atomic or molecular elements. Okay, and then the last one is conductivity and heat. Metals are good conductors of heat and electricity. Nonmetals are poor or not conductors of heat and electricity. Okay, isotopes. Know the definition of isotopes, and I'll tell you what that is if you want. But I mean, just look at that. But it is the same atom with a different number of neutrons, right? Same atom, different number of neutrons. And because it just naturally occurs like that, right? Different number of neutrons, different molar masses, right? Slightly, or different atomic masses, basically, right? The example I gave you guys in the notes was magnesium 24, 25, and 26. 12 protons, 12 neutrons, 12 protons, 13 neutrons, 12 protons, 14 neutrons, just how they naturally occur, okay? 4 properties of metals versus nonmetals and isotopes definition. Different number of neutrons, okay? Next, Bohr diagram. You remember the Bohr diagrams because they are boring. Nah. So, Bohr diagram. Maybe I should do this one with you guys. I don't remember. Let's do that. So, Bohr diagram. Let's do sulfur, I guess. Don't forget sulfur goes here, of course. You look over at sulfur. This comes back to protons, electrons, neutrons, right? So you look at sulfur. It's got 16 protons. It's got a weight of 32.07, so we'll say 32. Round it. 16 neutrons. That's your weight there, right? Protons, neutrons gives you the weight, 32. That's the nucleus. First energy level, 1, 2 can hold in the first energy level. Second energy level, 1, 2, 3, 4. Remember, they take positions as far apart as possible, and then they start to double up, right? So that's 4, 5, 6, 7, 8. All right? And what's that called again? What's that special thing that allows them to double up like that? What's that? Octet Rule, yeah. But more specific, there's another definition, another thing that we took that it says that basically we're allowed to do that. We can do that. We can double them up. We can pair them up. We can pair up some electrons. We can electron pair, yeah. Okay. Huh? Vesper, valence shell electron pair repulsion theory, yeah? Okay, so Vesper says they take positions as far apart as possible, but then we're allowed to, there's a unique thing called Vesper, valence shell electron pair repulsion theory that allows them to double up, okay? So that's 8, that's a total of 10, by the way. Here comes 2, 3, 4. Remember, we need 16. Right now we have 14, so we double up the last 2 here, right? So 15, 16. There we go. 16 protons, 16 neutrons. Full shell. Okay? If sulfur was going to become more stable, what would it tend to do, do you think? Yep. Gain 2 electrons. And they would probably go right here, of course, right? They'd want to go there and there, correct? Okay? And then that's why it forms, why does sulfur form a 2- charge? Because it wants to gain those 2 to fill out the outside shell. Okay? Electron energy level diagram. So, sulfur. We have the protons and the neutrons. Okay? That's the nucleus we put there. Protons, neutrons, and then we just work up from there, right? So first energy level has 2, second one has 8, next one has 6, okay, for a total of 16. Okay, and finally, the ever famous Lewis diagram, and I'll do Lewis diagram here. Let me make it farther up here, okay? Has everyone got the electron energy level diagram there? Is that okay? Lewis diagram, or electron dot diagram, is another term for that. Remember, just the valence electrons. So how many valence electrons do we have? You can just simply count over, remember. So 1, 2, 3, 4, 5, 6 for this case. 1, 2, 3, 4, 5, 6. Doubles up. Okay? I'll ask you guys the same thing. If sulfur was the central atom, what type of shape would it most likely form? Stephen? Yes, tetrahedral bent. AX2, E2. Here'd be your AX2s, right? Here and here, E2. So if that was the central one, that'd be tetrahedral bent. What's the bond angle for tetrahedral bent? Yes, that is correct, 104.5. Okay? Polar or nonpolar molecule if that was the central atom? Polar. It's got lone pairs on the central atom, it's polar, right? Okay, and we'll talk about some of that stuff coming up here. Okay, good. Other things that you need to be able to do. you have to be able to name ionic compounds and molecular compounds, okay? I'm not sure I'm going to have enough time for that with you guys, and I probably don't, but we need to name them and write out formulas for those. Ionic compounds, molecular compounds, both of those things. Let me just do this here real quick, okay? I will show you. I'll get out of your way here right away. Okay, I gave you a sheet like this at the beginning of the year, okay? And one had just naming and one had just formulas to do, right? So I would suggest you guys look over this sheet again here, writing names for ionic compounds, and then I was writing formulas for ionic compounds. It was double-sided. So make sure you look over that again, make sure you kind of review. You need to use Roman numerals in some cases, right, for ionic compounds, depending on the charge, if there's more than one charge, things like that. So look over that, please do, because I'll probably give you 3 or 4, maybe even 5 naming questions. That's just it, okay? So that could be a kind of a big chunk. We can't forget how to name compounds. That's kind of important. Or write formulas for compounds, okay? So make sure you do that, okay? So writing formulas for those, have to be able to do those, okay? Then we have drawing stuff, okay? The first one we'll look at is ionic. So when we get to ionic compounds here, okay, drawing ionic compounds. Don't forget, when you go to draw an ionic compound, you need to show me electrons moving, okay? Electrons are being gained and lost. You need to show that to me with arrows, okay? So I just picked magnesium chloride. Step 1, always write out the formula first, because that tells you how many of each one you need, all right? In this case, if I had just written out magnesium chloride, the first thing you should do is say, what is the formula for magnesium chloride? MgCl2. Write out the formula. I know I need 1 Mg and 2 Cls. I draw their Lewis structures, and then I show matching up, right? And if you do it correctly, remember, look, each one of these electrons here, that one there and that one there, have a home to go to, right? Just go to your home. Why don't you go to your home? Happy Gilmore, okay? And then they end up here and here, for example, to fill that octet, right? Magnesium is more stable. Chlorine, which now becomes chloride, is more stable as well, because they have 8 in each one, okay? Good, yes? Ionic compounds, you need to show me that. I tell you right now, if it says, if the multiple choice question says something about drawing ionic compounds, you look for something with brackets and charges, yeah? Nothing else. If it's ionic, you got to show me giving and taking electrons, right? If it's molecular compounds, then you want to show me sharing. Well, that's that kind of thing, right? Where we're sharing electrons. So you're going to write out the formula again. If I give you nitrogen trihydride, because we use prefixes with molecular compounds, if I give you nitrogen trihydride, we're going to write out the formula. Okay, you might want to start with some neutral atoms and link them together if you have to. Okay, so you'd put N in the middle because it forms the most unpaired has most unpaired electrons, best bonding capacity, yes. And you would kind of do that, right? And you would hook them together or whatever the case may be. Okay. Okay, so next, we need to draw polyatomic ions. And actually, I probably should do this one with you here. Let's get rid of this. Okay, so actually, let's get rid of even this part here. Once again, the very first thing you should do is write out the formula, right? So if I had said, I want you to draw the carbonate ion, or what does the carbonate ion look like? I would say, okay, carbonate is CO3 2-, start. how do you do these ones? Remember, you got to add up electrons, yeah? Yes. So we're going to go 4 valence electrons. Each oxygen has 6, so that's a total of 18. This particular CO3 has gained 2 more, so we need to add on another extra 2 here, right? 2 minus charge means it's gained 2 electrons, so we want to count for those 2. So that gives me a total of 24 electrons. Good? Yes? Okay. If it was a positively charged one, that means I need to subtract an electron, yeah? Okay. So if it was NH4 plus, I'd want to take an electron away, all right? So what do we start with here? We start with a skeleton structure, C, O, O, and O, for example. And we start joining the molecule together. So between the atoms first, we go 1, 2, 3, 4, 5, 6. Okay. After that, we want to go to the outside atoms first. So that's 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. And we've used up all the electrons. And then we have to stop and say, do we have 8 electrons around each atom there? And the answer is, well, the oxygens do, but the carbon doesn't. So how are we going to fix that? If you did have, by the way, if you did have 2 electrons up here, you would be done, yes? You just put brackets around it, charge, done. This one doesn't have, so we have to move stuff, okay? Not all the time do you have to move stuff, but sometimes you do. So you're going to take a pair out, and you're going to put it in there. The best diagram for this is probably going to look something like this here. Just to save a wee bit of time here. Okay? Like that. Remember, everything tries to spread themselves out as far as possible, right? Electron pairs repel each other, etc., etc. Okay? So that's probably your best diagram here. Don't forget, if you're drawing an ion, a polyatomic ion, you need to put brackets and a charge. Once again, if there's a multiple choice question and it says, which one of these is the carbonate ion, and you see some that don't have that, brackets and a charge, then don't pick those, okay? Because they have to have brackets. That's how we draw ions, and the charge, okay? So remember that. I think we've actually done this one before. If you remember on Unit 1 test, I think that was a question for you guys, except that we used dots instead, which, if you, whatever, right? Every line's a dot. We had a dot like that, and it might say, which one of these is the correct one for carbonate? You may not even have to draw it. Like, you know, like I drew that, obviously, but you might not have to draw it. You might just have to look at it and say, does everything, which one doesn't have 8 around it? Make sure everything has 8 around it. Make sure it's got the right charge there. Make sure it's got brackets. All that stuff, okay? We just have to make sure that, you know, like I said, it matches up. So you might not have to draw it, but you still have to understand the concept of what polyatomic ions look like, okay? So you might be able to figure it out without drawing it, is what I'm trying to tell you. Look for octets around each atom, of course. Look for charges and brackets and things like that, okay? You may have to count up the electrons to make sure you don't have extra ones. So you want to be careful of that. The carbonate only has 24 electrons to go around. So if one of them had 22 or 26 or whatever, you don't have enough, okay? So just keep that in mind as well, okay? Next. I'm probably not going to ask you a lot about properties of stuff. Having said that, once again, we should know that ionic properties, things that go on with ionic compounds, are obviously a crystal lattice structure. Opposites attract, plus minus, plus minus, plus minus. Crystal lattice, that's called. That would be the shape of the ionic compound. All ionic compounds are crystal lattices. Okay, ionic properties. So there is a list of ionic properties there that you probably, like I said, probably not going to ask you, but you should know them. Okay, you know, when we talk about conductivity and things like that, which we talked a little bit about in this unit as well, Unit 3, but in Unit 1 we talked a little bit about conductivity, things like that. Okay. Next, ionic bonds. You should know what an ionic bond is. Okay, so you should be able to, I guess, define it, which I know I gave you that definition for ionic bonds. And simply put, it's a metal that loses electrons, non-metal gains electrons. So there's a give and take, right, of electrons, so that they balance out, right, so that they become neutral molecules. So ionic bonds is giving and taking electrons. Covalent bonds. Okay, this might be a good definition thing here. Covalent bonds, of course, are the sharing of electrons. Covalent, sharing. And then we can even get more specific after that. So covalent bonds, you know, sharing electrons is what you want to look for there. Polar covalent. Polar covalent, of course, is sharing electrons, but not equally, right? If you're looking for a polar covalent bond example, you know, even something like this here. Okay, polar covalent. Has a negative end, has a positive end, not sharing electrons equally due to difference in electronegativity, right? Due to a difference in electronegativity. So maybe you want to put in here, actually En probably fits into there actually, but electronegativity, right? Maybe you know the definition of that. Once again, I don't think I'm going to ask you that, but I guess you never know. Polar covalent, though, would be something like that, not sharing electrons equally. Non-polar covalent would be something like that, sharing electrons equally due to the same electronegativities. Okay? So, non-polar, an example of that there. Okay? Good? Questions? Okay. Like I said, these are the basic things that you need to kind of take and probably apply to questions, yes, but the questions are going to be pretty straightforward for the most part. Then we need to get into, we talked about a little bit about the shape of ionic compounds, crystal lattice. What about the shapes of molecular compounds? So we need to know all those, okay? There is 6. Yes, 6 molecular shapes. Maybe I'll put that on there. We need to know the bond angles. We do need to know, well, the general formula. I'm not going to say what's the general formula of water, for example, AX2E2. I'm not going to ask you that. However, if you know what's AX2E2, maybe you can say, oh, that's tetrahedral bent, and that's 104.5, and that's probably polar because it's got E in the formula. So that might help you there instead. Okay, so 6 molecular shapes you should study. Bond angles of those. Remember, I gave you a chart. Actually, there's a page that summarizes all that for you that I gave to you guys, and I said the only thing that's missing on this page is the bond angles. If you wrote that down, you'd have an excellent study sheet. Okay, so that should be in your notes there, and I know you have it. Okay, just a quick example here. CH4. Okay, was just one that that's all I had time for last class. CH4, so we of course say that's AX4, that's tetrahedral. Oops, yeah, sorry, that's 109.5 for the bond angle, tetrahedral. And then that one happens to be a non-polar molecule because all the X's are the same, it's symmetrical, right? And then I put down here, by the way, AX2, AX3, AX4 can be nonpolar if the X's are all the same. Okay? Otherwise, if they're not all the same, then it's most certainly polar. And of course, anything with an E in the general formula is automatically polar. So I might want to put that here. E in, actually no, I'm going to put that somewhere else because here's just a quick few examples of nonpolar molecules. Okay, CO2, CH4, BH3. Okay, are examples of nonpolar. molecules. All right. Polar molecules. Okay, well, if we take one of those off and we put something else on there in place of it, it'd become polar. So if the X's are not the same, polar, E in general formula. Okay, so like for example, AX3E would be polar, most certainly. Okay, so AX3E would be polar, or AX2, but the X's are not the same. So I'll give you I'll give you an example of this one. Probably the most famous one that we know, NH3, is an example of AX3E. That's polar, most certainly. Lone pairs on the central atom, polar. Another example might be AX2, and we'd have to, of course, make sure that we have something like that, where the X's are not the same. AX2, but the X's are not the same. Okay? That would also be polar. All right? Because a difference in electron, remember, the electronegativities have to cancel each other out, and they would not in this case. Okay? They'd have different electronegativities. All right? Is that good? How are we doing so far? Yeah? Good? Okay. Probably the next thing we need to talk about then, the next biggest thing, of course, is you need to know the definition of intra and intermolecular forces. Intramolecular and intermolecular. I'll give you a very standard definition here. Holds one together. Holds many together. I wanted to put something here. Melting points and boiling points, for example, is a result of intermolecular forces. Okay? Remember, we have to break intermolecular forces to melt or boil substances. All right? So when we talk about that, we're talking about intermolecular, melting points, boiling points. All right? The intra, what holds one molecule together. Inter, what holds many molecules together. Okay? I gave you this chart here as well, very, very important chart. And yeah, you'll probably have one or two comparison ones to do. So once again, we have ionic and metallic at the very top, right? Opposites attract, very strong, right? Right? Ionic and metallic at the top, very strong. We then get, I'll let you guys copy this down first, maybe. Once again, ionic metallic, very strong. Molecular, comparatively weak, right? Underneath molecular, we got things like hydrogen bonding, dipole-dipole, London forces. And London forces, of course, are based on two things, size and shape. All molecules have London forces. Yeah, so if it comes down to that, that might be the deciding factor. However, when we talk about hydrogen bonding, that's for polar molecules. Hydrogen bonding is H bonded to NO or F, of course. Dipole-dipole is basically anything that's polar, but not H bonded to NO or F. And London forces is the only thing for nonpolar molecules. Remember that these are permanent dipoles. Permanent dipoles, these are temporary dipoles due to electrons spinning round and round. Okay? So, when you go up this chart, melting and boiling points increase, aka strength of the intermolecular forces increase. Okay? So, the stronger they are stuck together, the more energy you need to break them apart. How do you give them energy? Well, you heat them up usually. That increases the melting or boiling points for them, right? So the ones that are stuck together very well tend to be higher solid forms. The ones are kind of in the middle are liquid forms, and the ones at the bottom are kind of gas forms. Okay. For example, F2. Okay, F2 is FF, nonpolar. All right, it's a gas. Look, it's in red there. It's a gas. It's only got London forces. Okay, so that's why it's kind of at the bottom. Very small size, shape, yeah, linear-ish, but whatever. Okay, so it depends on lots of factors, of course, but all things being equal, remember we need to be able to slot molecules into this part, right? So if I said pH3, where would that fall into here? Well, is pH3 ionic or metallic? And you'd say no, because it's full of it's just nonmetals, pH3, right? Is it molecular? Yes. Does it have hydrogen bonding? You'd say no. Is it polar? Is it a dipole-dipole? And the answer is yes, because when you draw pH3, it's got a lone pair on top, right? That's why drawing them is very helpful, of course. You'd say, oh, that's polar, AX3E, polar, dipole-dipole, right? And let's say you're comparing it to, let's just say ASH3, for example. We did this one before, of course, guys. But if I give you a list of molecules, you should be able to sort them out, or at least tell me which one's the highest, or perhaps the lowest boiling point, or melting point, right? ASH3, you'd say, once again, okay, so you'd say AX3E for both of these, of course. Now, they don't have to be the same, but once again, you need to slot them in. So ionic metallic, no. ASH3, no. Hydrogen bonding, no. Dipole-dipole, yes. So they're both dipole-dipole, right? And then we say, well, okay, which one's going to be stronger? Don't know. So I got to go down to London forces, size and shape. Well, they have the same shape, so it comes down to size. This one would be stronger because it's got more electrons, more temporary dipoles, and because of that, it's stronger. Okay, so we spent some time doing that in that lesson at the end there. Okay, and if you want more practice on that stuff, obviously come and see me, and we'll do that on Tuesday. Okay. All right. So intermolecular forces and stuff like that, and that's pretty much it. Having said that. Obviously, that's a very general kind of thing, okay? You really need to spend some time and kind of go through those notes and go through what I kind of went over on the board here and do some practice questions on those things, okay? There's lots of practice questions. I gave them to you in your thing. Pick one, do it, see if it matches up, or at least look at it and see what's going on here, okay? But you need to spend some time. Just don't study this, okay? That was pretty quick, and I didn't tell you everything. I said, know the definition of this, the definition of that. Go back through, write some stuff out, okay? Make cue cards, whatever works for you. But we need to make sure we can do that stuff, all right? Let's see here. I'm just trying to think if there's anything else I kind of forgot. Once again, okay? There is probably one other thing that I'll just put on here, and that's just properties of metallic, ionic, and molecular compounds. Okay? So just think about those properties as well. And in fact, at the end of the very last lesson is just the properties of that stuff. I don't think we're going to have, I would say a very, maybe one question or maybe two, but it might help you with some of the other questions as well. So I don't want to discount that. But properties of metallic, ionic, and molecular compounds you should know, okay? Especially the things like conductivity, okay? Which one of these conduct electrical current, which ones don't? What form do they have to be in to conduct electrical current? And the other thing at the end was, of course, conductivity we talked about. Oh, and physical properties. So mechanical properties we call this. So what happens when you hammer on an ionic compound? What happens when you hammer on a metal? What happens when you hammer on a molecular compound? Okay, things like that. All right. Once again, the midterm on Tuesday is going to be pretty straightforward, I think. That's Wednesday. Well, I don't know, what did I say? Oh, wait, Wednesday, the 13th. Ooh. It's going to be pretty straightforward. Having said that, we need to study, right? This is, the thing with this one is, this is the only one in that category for midterm. There is only one midterm, okay? So it's not like you're going to average this one out with the rest of them. I mean, at the end, yes, you do, but it is the only midterm category, okay? It's going to be pretty basic questions. I'm going to tell you right now. There's going to be, once again, probably close to 30, because I don't want to, I like to give you a little bit more than anything, and if we have to take a little extra time, that's okay. But it's going to be pretty basic questions, about an even split, so 15 and 15, and the Unit 2 stuff that we have on there is going to be basic stuff like, you know, PV equals nRT, P1 V1 T1 equals P2 V2 T2. Probably get a graph on there, I'm sure, of something, Gay-Lussac's law, Charles' law, or Boyle's law. Things like that. They're going to be very similar questions to probably what you kind of saw on the test. Okay, not too much different than that. All right, so you kind of know where you're at with that. Tuesday, if you want any help, I will be here early on Tuesday at 8, and then we have scheduled help lunchtime and after school if we need to. Okay, and then Wednesday's your midterm.